at Northwestern University, USA. At IIT Madras, Dr. Vinugar leads an active research group that focuses on thermochemical conversion of a variety of feedstocks such as biomass, waste plastics, algae, municipal solid waste, and low-quality coals to liquid fuels and chemicals. Dr. Vinugar has demonstrated the use of low-power microwave-assisted pyrolysis technique for the production of liquid bio-oil, non-porous biochar, and carbon nanotubes from renewable and non-renewable feedstocks. Dr. Vinugar has published over 100 scholarly research articles in various international journals and book chapters. He is the recipient of Young Engineer and Young Scientist Awards of prestigious academies and institutes like IEI, ICT Mumbai, INSA, NASI, IICG, IIC Bangalore, and IIT Madras. Dr. Vinugar also serves as editor of Advanced Powder Technology and editorial board member of Journal of Analytical and Applied Pyrolysis. Thank you.
Thank you, Venkatrao. May I now request Dr. Venu Garu from IIT Madras to deliver his lecture on hydrothermal liquefaction in the Indian context. Voice important, Sarthi.
మ్యూట్లో ఉన్నారు సరే లేదా సార్ అడగండి
Sir, your voice is not audible, sir.
ఇంకెలా పెట్టేయండి తను మాట్లాడండి ఫస్ట్
Hello? Am I audible? Hello?
Yeah, now it is audible, sir.
Yeah. Just a moment. Sorry for that.
Yeah, no problem.
I have just changed my laptop. So
Now this is perfectly all right, sir.
yeah. I'm joining. Yeah. Just a
Yes,
moment.
sir.
Okay, shall I get started?
Yes, sir.
Yeah. Okay, is my screen visible to all?
Yes, sir.
Yeah. Okay, sorry for the initial delay. I think the issue was on my side. Okay, so sustainable solid waste management, and this is going to be typically presented in the Indian context because we are now facing, huge issues waste management in the country, and it is very important that we are able to address them using technology, which is agenda. So initially, I'll talk about what are the municipal solid waste, single-use plastics, agro-residue waste, which are constituting the entire solid waste in the country. What are the challenges and how are they different from the Western waste, right? And then I'll talk about hydrothermal liquefaction, some of the results that we have obtained in the past on HTL of biomass and solid waste. So this is the focus of my, coal, right? Just as a representation of conventional feedstocks. And we deal with a wide variety of thermochemical processes, not only hydrothermal liquefaction, but also pyrolysis. We employ a lot of catalytic transformations and also product such as biofuels or syngas, phenols, aromatics, right? And also energy, typically renewable energy. So this is the broad theme of what we work in my research group. Coming to the typical context of renewables and waste conversion in India, right? It is well known that we are the third highest producer of agro residues after China and Brazil, and we have a surplus potential of 235 million tons per year as on 2017, right? And we do have a wide variety of agro residues in the country, right? And these are the top agro residues, and of course we all know that open field burning of rice straw is going to create a lot of problems because it results in a lot of nutrient loss such as carbon, nitrogen, phosphorus, potassium, and it also leads to a lot of particulate emission in the and this usually occurs every year around October, November, right? Or typically during the harvest season of 1 month when a huge amount of these rice straw remains are going to be burned, right? And we are only short of few weeks from now to hear such news, in the media, right? And what are we really going to do about it, right? Even though there are a lot of technologies, it's a combination of both. A technological solution, providing a technological solution, and also a solution that is more sustainable in a longer run, right? So this means that we need to really tackle this in different using different technologies at different scales in order to make sure that we are able to do this in a more sustainable way and also reduce the pollution. And apart from this, we are also, having a lot of different types of agro residues, like the Prosopis juliflora. It's a very important native very important invasive species found in the country in a very widespread way. Right? And we all know what is a biomass. I don't think I need to emphasize this, right? Biomasses or agri-residues or the second generation feedstocks contain cellulose, hemicellulose, and lignin as the major components, right? And any treatment technology is going to result in decomposition of these carbohydrate and lignin based matter, and it is going to produce fuels and chemicals, okay, which can contain phenols or aromatics or hydrocarbons and so on, right? And typically now we have a huge variety of biomass sources. So biomass is a very common term, and we are actually having a lot of different sources, not only lignocellulosic agro residues, but also forestry residues and crops. We have industrial residues like effluent treatment waste, right? Animal residues like cow dung and different litter by the animals. Municipal solid waste, it would contain some fraction of biomass, but not completely biomass, but it also contains a lot of plastics, right? And also the sewage, the fecal sludge and things like that. Okay, so as a result of this, right, we need to tackle all these different types of waste in a very efficient manner, so that we are able to produce the value-added products in a very sustainable fashion. So in addition to agro residues, we are also facing a significant municipal solid waste management and solid waste management issues in the country, right? I mean, these are some of the common scenes. For example, this is not only restricted to Delhi, but also in many other parts of the country. In major cities, we have due to the dumping of the waste, the solid waste, domestic as well as industrial waste in landfills. A lot of these landfills are getting converted to dump sites, okay, without a proper management of these waste, right? So there are a lot of these types of dump sites available across the country, and every municipality, every corporation is trying the best ways to make sure that these are handled and kind of converted in every possible way. So typically, India generates significant amount of solid waste. A majority of them ends up in landfills, and the per capita generation is around 0.5 to 1 kilogram per person per day. Okay? So unlike MSW of Western origin, how our waste is very different, right? So unlike MSW of Western origin, Indian MSW is highly heterogeneous because it contains a lot of domestic food waste and bioorganic waste, right, which result in significant amount of moisture in them, right? Because of very high amount of moisture, right, the calorific value is going to be very low. And apart from moisture, it also has a lot of inert materials, okay, such as sand, glass, the canisters, metal canisters. So a lot of these constituents are going to be present in our Indian MSW, that is going to be like unsegregated as present in the landfills, right? And this is a typical example of the waste from a specific locality in Tamil Nadu, from Trichy, right? Here you can actually see that the food waste constitute around 32%. Then you have garden waste, paper, and cellulosic waste, and then you have plastics typically constituting 15%. And one of the unique aspects of the Indian MSW or Indian unsegregated waste is it does contain significant amount of this coconut shell, right? And this is like a dry basis composition, right? You can see a lot of different components that are going to be present in the waste, right? And generally, on an average, in India, we can say that the solid waste is going to contain 50% of the biodegradable waste, and the rest is all going to be, all the other components such as garden paper, plastics, and so on, right? And if you take the statistics in every state, right, it is going to be somewhat like this, because a significant fraction is not treated, and majority is kind of landfilled, and this results in, mounting of waste in a lot of these dump sites, right? And the conventional technologies that are practiced, for example, in Tamil Nadu is that, composting. Typically, the organic wastes are treated very well, but the inorganic waste, the plastics, are not so well treated, and this is what really ends up in the landfills. And what are these plastics? A majority of these plastics are essentially single-use plastics, which are constituted by the packaging waste. Okay, and a very good report by UN on single-use plastic is available. So if you want, I mean, this is like freely downloadable. You can actually download and understand what are the waste generated by different countries, how different countries are practicing, and what methods they are practicing to minimize the use of single-use plastics, and also how they are treating the thrown away single-use plastics. And what are these single-use plastics? Most of them are high calorific value materials like low density polyethylene, high density polyethylene, PET, polyethylene terephthalate, polypropylene, polystyrene, and expanded polystyrene, right? So all these belong to a specific class of olefinic polymers, right? And I mean, there are like strategies available to convert them to the fuels and chemicals, because the pyrolysis, for example, can actually result in the production of hydrocarbons, and it is possible to make sure that we are able to derive value out of them. But what is the challenge? Where does the challenge lie? Okay, the challenge lies in the fact that majority of these are going to be completely mixed along with the different type of waste. Okay, first of all, you need to have a good segregation at source. Even though it is practiced, I mean, we are having a lot of awareness these days about segregation of plastics at the source, but still it is not really widespread, right? And there is already a significant amount of waste plastics in the dump sites. Okay, so are we going to implement some kind of an infrastructure to segregate the waste in the landfills, and then are we going to process each of these waste in specific using individual technologies? Or we are essentially interested to know if we can treat all these waste as it is and then produce a product which can essentially be used, okay, such as in heating, or whether it can be used in refinery based applications and so on. So that is where we come from. Okay, so to summarize the motivation, right, it is very evident that there is a paradigm shift in solid waste management today. Okay, because what was once thought of as a best practice, which is landfilling, is no more the practice today. Okay, because we want to now do a lot of source reduction, we want to do a lot of recycling and composting, and we also want to implement significant technologies to make sure that very minimal amount of waste ends up in the landfill. Okay, so what is the aim? Okay, the aim should be to generate energy or fuels or bioproducts from waste, but not really waste from energy. Okay, so what I mean by this is, a lot of these solid waste that we are talking about are high calorific value or reasonable calorific value waste. That means they do contain some energy. Okay, so it is important that the net energy consumption of the process, okay, should be at least neutral or positive. For example, the total energy that we are going to derive from the waste, from the products, okay, from each of these conversion technologies, okay, should be more than the energy that we really spend in order to generate the specific product or biofuel. Okay, for example, a classic example is, is the energy generated greater than the energy consumed by the trucks that move the garbage to the site? Okay, that means our energy assessment, okay, should be based on a very holistic. It should be a holistic analysis. For example, we should include the energy that is consumed, or the fuel that is consumed, because the trucks today consume conventional diesel fuel or hydrocarbon based diesel, okay, in order to move the material or the waste that are generated at different sites to a common place, right? So a simple analysis like this can really say whether we are actually generating a positive energy, okay, or at least we are just equalizing the energy that we put in and the energy that we derive out of the process. Okay, so these are some of the key points that we need to take into account when we talk about the conversion technologies and assessing the sustainability of these technologies. Okay, so I would like to basically say that today municipal solid waste are emerging as the fourth generation feedstocks. Okay, so you might all know about the first generation feedstocks, which are usually edible crops or edible products. Okay, such as sugarcane juice or cassava or corn. Okay, which were used to produce bioethanol or biodiesel. Right. Then came the second generation feedstocks, which are mostly residues. Okay, we are still in the phase of converting these agro residues to bioethanol, which is now being implemented at a large scale in India, right? And then we have the third generation feedstocks. Algae used to be called as the third generation feedstock because we can actually derive a significant amount of lipids, proteins, and nutrients from algae. Okay, but now today, because of the solid waste that are being generated in excess, right? We have to tackle them, and we have to make sure that these fourth generation feedstocks are tackled using multiple technologies to make sure that we are generating value out of them. So I'm kind of presenting this in a very holistic picture, okay, where we see this as something like X to liquid technology. So we are primarily interested in producing liquid fuels, from a wide variety of waste, agro residues, and even conventional feedstocks like coal. Okay, so these two are something that is well researched, well known. Okay, so you can convert sugar, starch-based crops. You can do an extraction fermentation to produce bioethanol type fuel. Oils and fats can be transesterified to produce biodiesel. Okay, these two are well-known technologies, right? But if you think of agro residues like lignocellulosic biomass and forestry residues, you can employ any thermochemical conversion technique like pyrolysis, gasification, hydrothermal conversion, or even combustion. Combustion can be used to generate energy and power, but typically the pyrolysis gasification type technologies can be used to produce liquid fuels. Waste plastics and polymers can be pyrolyzed to produce liquid fuels, like Msw, RDF, waste oils can also be pyrolyzed, and we can even do a hydrothermal conversion, right? And micro and macroalgae can be converted, and even coal can be converted to liquid fuel, so that the liquid fuel is more like a storable form of energy, right? That can be like easily transported and also used in a wide variety of applications, such as in engines, generators for power generation. It can be upgraded and can be converted to a fuel that can essentially be blended with existing fuel, like gasoline, diesel, kerosene, and other type of fuels, or it can be converted to valuable intermediates and fine chemicals. So based on the type of feedstock, we can actually choose the technology today and then produce different products, right? But the main key factor is that we also need to understand the economics of each of these processes, and the scale, the effect of scale in actually bringing down the cost of the liquid fuel we are producing per liter or per kilogram. So if you look at all the strategies for biomass and waste upgradation, right? The Van equivalence plot is a very, very important way of assessing how much of an upgradation that we are going to make. Okay, if you really see all these conventional fuels, right, we can actually say that the biomass, solid waste, cellulosic waste, all those contain significant amount of oxygen. So their atomic oxygen to carbon is high. Okay, that's primarily because biomasses contain the cellulose, hemicellulose type of materials. So if you now want to convert them to gasoline, kerosene, diesel, okay, which do not contain any oxygen but typically contain carbon and hydrogen at a ratio of 1:2, right? We need to do significant amount of deoxygenation, and then we also need to do what is called as a hydrogenation. Okay, because deoxygenation means we want to remove oxygen from the material, but removing oxygen can be done only by removing oxygen in the form of carbon dioxide or carbon monoxide or water. Okay, that means for every atom of oxygen that is removed, we are also losing some carbon or some hydrogen, right? As a result, right, we need to do both hydrogenation along with deoxygenation, or we need to do what is called as a hydro-deoxygenation. That's like a combined hydrogenation and deoxygenation in a single step using catalysts that can produce hydrocarbon-based fuels. So coming to the topic of our process, okay. So one of the key challenges with a majority of the thermochemical technologies like pyrolysis or gasification is that we need the feedstock which is going to be dry. Okay, that means the moisture content has to be like lower than 10% or 15%. Okay, so that we are not actually spending significant amount of energy to simply dry the feedstock. Okay, so one of the key processes that can be used to produce fuels, okay, let's say liquid or solid fuel from wet feedstocks, okay, such as solid waste, which can contain more than even 60-70% of moisture, or even fuel feedstocks like algae, which are essentially grown in water bodies, right, is that we can actually employ a technique called as hydrothermal liquefaction. Okay. What is hydrothermal liquefaction? It's very simple, right? It's a method that mimics Mother Nature, okay, in producing fossil fuels. Okay, typically fossil fuels like crude oil and coal are being generated underground, okay, over millions of years, okay, through the application of high pressure and temperature. Okay, we are trying to mimic the same thing in a reactor, okay, by maintaining subcritical conditions. Okay, so typically this is the pressure temperature diagram of water, where you can see that this is going to be a critical point, okay, which is 22.1 megapascal and 374 degrees. So what is very evident here is that when we are going to operate at subcritical conditions in this regime, right, we are actually going to maximize the output of our liquid product, okay, and minimize on the solid products. Whereas if you go beyond a temperature or beyond the critical point, it's going to result in catalytic gasification that can result in simple generation of gases like hydrogen, methane, carbon dioxide, and so on. Okay, so by operating at this condition, what is going to happen is, this is the property of water at the critical condition. What really happens is that at these conditions, water acquires the property of an organic solvent, right? And you can see here that the density of the water is going to be similar to that of an organic solvent, right? It's not going to be simply 1,000, but simply something like 600 to 700 or 800, right? And its dielectric constant is also going to reduce. That means water is going to act as an organic solvent, and it can essentially decompose the organic matter that is constituted by the waste. And we can also see that the ionic product of water, okay, which is denoted here by Kw, right? This is nothing but the ability of water to form hydronium ions and hydroxyl radicals, okay, that is H3O plus and OH minus is going to be significantly high, okay, at these conditions. As a result of this, what happens is water can actually act as a catalyst, and it can decompose the solid material, and that can result in very high quality of the product with very high calorific value and very low oxygen to carbon content. So you can think of this process as a pressure cooker, okay, a very large pressure cooker in which we dump the material, right, and then close the vessel, right, and increase the temperature and pressure to these conditions, and hold it for 30 minutes to 1 hour time period, right, and finally we can expect to get the bio crude, or we call it X crude as the product, right, and we also get biochar, which is the solid residue that is formed during the process. So the quality of the crude and the yield of the crude and the char will significantly depend on the type of feedstock that we are actually using in this process. So this is just a comparison of our bio crude with the pyrolysis bio oil. Okay, you might know that there is the pyrolysis process essentially produces a liquid product called as bio oil, right? Which is going to be which is also going to mimic a liquid fuel that we are deriving from agro residues, right? So we can actually say that the bio crude contains significantly low moisture content. It has high carbon, right? Very low oxygen, and so it has a very high calorific value compared to pyrolysis bio oil. So it has a lot of advantages, but the major disadvantage is uh, uh, you know the major disadvantage is it is highly viscous. Okay, its viscosity is very high, and so it is not very easily flowable. Okay, as a result, there are some disadvantages with biocrude which we need to tackle with just to make sure that we are able to utilize it as a liquid fuel. Okay, so if you really survey the literature, right, there are a number of studies that have been performed on hydrothermal liquefaction of different feedstocks such as lignocellulosic biomass, solid waste, okay, such as pig manure, sewage sludge, food waste, right? Microalgae, okay, some of the microalgae are given here, and a lot of macroalgae, okay, which are essentially seaweeds. Okay, what we can essentially see here is, the quality of the biocrude is improved compared to the feedstock because it is highly deoxygenated. Okay, so starting from 0.8 O by C ratio, we are actually coming down to 0.2 to 0.4 O by C ratio, and you can see that more than 50% deoxygenation is achieved in with regard to in the case of different types of solid waste that we are employing in the hydrothermal liquefaction process. Okay, so coming to some of our results from our lab. So we have been working in this area for about for about 3 to 4 years, and we have been working with a wide variety of feedstocks using hydrothermal reactors. So this is a typical setup of the hydrothermal liquefaction reactor. Okay, this is like a lab scale autoclave. The picture is actually shown here. Okay, an electrically heated furnace with pressurizing setup, and it is like continuously stirred using a magnetic drive based stirrer, right? Typically the pressure and temperature are controlled, and there is a valve to withdraw the contents of the reactor after a specified period of time. Okay, and the typical process basically involves charging the material. Because the reaction is conducted in subcritical pressures of water, we need to also charge water. So that means we need to make sure that our solids content is within 10 to 15%, and the rest being water. So we can even use wastewater. Okay, we can even use seawater. So we are actually evaluating a lot of different possibilities so that we can reduce on the cost of water that we want to actually use in the process. So typically we add the contents, pressurize the system with nitrogen up to some initial pressure, right? And then we close the contents and then heat, right? As we heat the reactor contents, right, the pressure buildup is going to occur inside the reactor, right? And so there is going to be an autogeneous pressure development, right? So the pressure increases as we increase the temperature, and once we reach the final conditions, we can always hold it for some time and then stop the reaction. Okay. So going further, this is the typical experimental and product separation protocol. So typically we can take our feedstock. Typically we can have water, and we can also use some kind of solvents as a co-solvent. okay, or an organic solvent like methanol, glycerol, or something like that, because we can always improve the yield of the biocrude if we are going to use some of these co-solvents, right? Then we charge the contents into the reactor, hold it for some time, right? And then we kind of release the pressure, right? And once we release the pressure, we can essentially take out the gases, collect the gases, and we can analyze the gases, right? And the reaction mixture is going to contain aqueous phase. It's going to contain the biochar and the biocrude all mixed together. So we need to kind of separate them, adopt some standard techniques to separate them. Okay, for example, one practice is to do filtration. Okay, on a larger scale, we can use a filter press, but on a smaller scale, we can always do a vacuum filtration, and we can also do solvent extraction using some favorable solvents like dichloromethane or ethyl acetate and so on. And then we can actually separate out the solid phase, the liquid biocrude phase, and the aqueous phase into 3 different fractions, and then we can evaluate their quality. So here I'm presenting some of our experience with hydrothermal liquefaction of Msw. So this is a typical solid waste that we collect from the MSW sorting center near Chennai, where we found that it has very good amount of volatile matter and a good amount of carbon content in it. So that means, it is a high calorific value feedstock, right? And then typically we adopt conditions, in the range of 300 to 350, right? Typical pressures, right? And in this study, we actually used water and glycerol as the solvent. So that means glycerol is a co-solvent which can actually use to enhance the solubility of the organics that are actually present in the products. So what we finally got was we got around 58% of biocrude and 32% of char. And you can see that the calorific value is of the char is reasonably good. It is kind of close to coal, whereas the calorific value of the biocrude is around 35 megajoules per kilogram, and it does contain significant amount of organics such as phenol, cyclooxygenates, aliphatic hydrocarbons, and so on. And the advantage is we are actually using one way to basically say that glycerol doesn't add really significant cost to the process is because glycerol is basically a cheap solvent. It is one of the byproducts of the biodiesel industry, so we can actually use even crude glycerol and mix it along with water, okay, so that we can use it as a cheap solvent, right? It's a zero cost MSW. You can see this is a typical composition of the waste. It contains a lot of some amount of the plastic matter. It does contain significant amount of the the biomass waste. A lot of cloth matter is present in this, right? And you can see that O by C achieved in the biocrude is 0.2, okay, all the way from 0.65 for the feedstock. And overall, we evaluated that it is a net energy positive product. That means energy of the biocrude and biochar was more than the energy of the feedstock. That is this feedstock and the heat that we supply in order to raise the temperature, of the feedstock and solvent mixture to the required temperature. And we also did a very, very thorough analysis wherein we studied the effect of temperature and also reaction time. Okay, so you can see that for every temperature, you can see that as we increase that reaction time, we can see that the char yield decreases and the biocrude yield increases. And we could achieve an optimum biocrude yield of around 58%. Okay, at 55% at around 15 minutes of residence time at 350 degrees Celsius, right? And we also evaluated thoroughly, right, the carbon number distribution, hydrogen distribution, and oxygen distribution in the product. So we can see that around at 350 degrees, carbon content, significant amount of carbon is recovered in the biocrude, significant amount of hydrogen is recovered in the biocrude, right? And we can also see that very less amount of carbon, oxygen is present. So that means, right, 350 is more like a sweet temperature that can result in good yield of the products. right? And we also thoroughly evaluate the organic composition of the product using GCMS, gas chromatograph mass spectrometer, and we can see that at 350 degrees, 15 minutes, we get a nearly equal amount of phenols and cyclooxygenates. So these are valuable chemicals from the viewpoint of the quality of the product and the materials, biomaterials that we can actually derive from them, right? And the content of aliphatic hydrocarbons can be increased if we go to very long residence times, because they tend to form at longer residence time at high temperature conditions. Okay, so we have actually expanded this for multiple types of feedstock. So here you can see the results for rice straw, where we use water and methanol as co-solvent. So you can see here that with 50-50 water methanol, right, compared to only water, we are actually improving the yield of biocrude from 12 to 31. And by adding a catalyst, okay, such as potassium hydroxide, right, we can even improve it up to 40%. Okay, so again, these are homogeneous catalysts. These are not heterogeneous catalysts, because using a heterogeneous catalyst can actually result in problems related to recovery of the solid phase catalyst. Whereas if you are going to use a liquid phase or a catalyst like hydroxides or carbonates that are easily soluble in water, right, we can actually improve the yield of biocrude significantly. Right, and you can see that the biocrude has very low amount of oxygen that is present in it when we start from rice straw. Right, and there are like some established mechanism of how these carbonates and hydroxides affect the deoxygenation process, which is what is shown here. You can see that by using potassium carbonate, right, it initially forms under hydrothermal conditions, it forms bicarbonate, right, and the bicarbonate can actually undergo decarboxylation, right? So similarly, potassium hydroxide can react with CO to form formate, right, and this formate can then produce bicarbonate. So there are like different ways by which these salts can actually react, okay, under hydrothermal conditions. So for example, here you can see that with potassium hydroxide, sodium hydroxide, and potassium carbonate, we see different composition of the biocrude product. So in one case, we are getting more of alcohols, long chain alcohols, whereas in other cases, we are getting a lot of phenols present in the biocrude. And even by changing the water to methanol composition, we can actually change the selectivity of the product. So for example, once we add methanol, we see significant amount of esters that are present in the biocrude, right? Because of a variety of the esterification reactions that occur when we are going to add, an alcohol like methanol as a co-solvent. So you can see that without any co-solvent, we get mostly cyclopentanones, cyclohexanones, phenolics, and aromatics, whereas with alcohol, we are getting a lot of fatty esters and aliphatic hydrocarbons in them. So the presence of a solvent can greatly affect the composition of the biocrude in terms of the reactions that it undergoes, right, along with the products that are generated during the process. Okay, so very similar thing with bagasse, and again we actually did a response surface type optimization of the process, where we actually optimize these are the optimization plots for the biocrude and yield of biocrude, and here these are the optimization plots for the yield of for the calorific value of the biocrude. So we could get a maximum yield of biocrude, which was around 36%, right? 36% was the maximum yield of biocrude that we could get, right? Using KOH at 10%, 15 minutes, and 320 degrees. While at the same conditions, just at 45 minutes, we got maximum calorific value of the biocrude. And here also we can see that phenols are the major products, and these boxes are phenols, and we do get significant amount of esters because we are using methanol as a co-solvent in the process. So finally, right, we need to make sure that the entire process is sustainable. Okay, so as I said, we are going to get an aqueous phase product right, which is going to contain some organics and it can also contain a lot of the uh, ions that are being transferred from the biomass to the aqueous phase. So here, this is a typical flow sheet of a process where we can actually recirculate the aqueous phase back, okay, so that we are actually able to do a process intensification in order to improve the product yields while minimizing the water requirement for the process. Again, as I said, I mean, even though we do use, distilled water during our experiments, we are also investigating how we can use impure water, okay, like typically an effluent treatment plant treated water, which is not really of drinking quality, okay, in this hydrothermal process. So in this process, what we did was we took the aqueous phase, took 80% of the aqueous phase, and then mixed it along with some makeup water, and then did this experiment multiple times to see how the product yields are going to change. So here you can see that initially this is our initial experiment with fresh water, and then we have recycle 1, recycle 2, and recycle 3. And here we see that the yield of the bio crude is decreasing, whereas the yield of biochar was increasing, right? And this was partly correlated with increase in potassium and chloride content in the aqueous phase with every recycle, because rice straw contains significant amount of potassium and calcium, which gets transferred to the aqueous phase during the process, right? And along with it, we also see significant amount of calcium and silicates being transferred to the aqueous phase that can actually alter the quality and yield of the products that we are generating from a material like rice straw. Right. So essentially, to give a summary, right, we are essentially expanding on the feedstock range, right? I've showed few results with rice straw, bagasse, MSW, right? We have also performed studies using defatted yeast, some of the macroalgae like Kappa ficus, spinosum, and so on. And overall, what we see here is there is a huge potential for the process to emerge as a feedstock agnostic process. Okay, this is a process that can actually take feedstocks that are really wet, right? And this can also take feedstocks that are significantly dry. So there is no limit on the moisture content that the feedstock has. Okay, so obviously, we are trying to go up in the scale, because most of our experiments so far have been with small scale batch reactors, and it is important that we establish the process with continuous reactors and also on a larger scale, so that it is easily adoptable by any industry at a later point of time, which we are trying to implement using our startup company. So here we typically take the MSW or the waste biomass, shred it, right, put it into a HTL reactor, and we get products which is a mixture of everything, right? We then separate out the aqueous stream. We can recycle the aqueous stream, right? Use a filter press. We can separate out the biochar, biocoal, right, which can essentially be used for combustion, which can be combusted to recover the heat, and the heat can be recycled back to the process. And finally, we can do a solvent extraction to extract the biocrude, right, for chemicals, fuels, blends, and other heating applications, right? So the salient features of the process are these. Okay, so it's a feedstock agnostic process, right? Any type of feedstock can be used. The application of the biocrude are many. Okay, this is something that we are also evaluating, if we can even blend not even 5 to 10, but at least 1 to 5% in crude oil, and see if it is going to result in what kind of changes it occurs to the final products or distillates. Okay, it can be fractionated, especially with macroalgae. We found that we can get significant amount of cyclopentenones. It can be mildly upgraded, to RFCC type feedstocks using a hydrogenation process. It can be converted to biodegradable plastics and biolubricants, although this is this is an area at a nascent stage. We are yet to really explore a lot more into this. And the most easy application is it can be blended with conventional fuel oil in furnaces, okay, for heating applications or power generation applications. And The greenhouse gas emissions, especially NOx, SOx, is very, very low because the operating conditions are such that, it involves high pressures and the temperatures are significantly low at around 350 degrees. So the generation of these gases like nitrogen, sulfur, or even polyaromatic hydrocarbons are in the gas phase are really minimized. So what happens is most of these components are getting transferred to the solid phase because of the high pressure conditions. And as I've already shown, it's a net energy positive process and it is capable of handling significant amount of moisture. Okay. So finally, to summarize, right, what I would like to emphasize is HTL is an emerging process, although a lot of lab scale R&D has been done. Right, there is a significant interest today in order to expand on this process and take it to the next level of pilot scale and demonstration scale. So that significant volume, significant amount of the waste can be converted to valuable products. So typically the products are in 4 phases. So you have biochar, which can essentially be, the simplest application is it can be combusted to generate energy, which can be recirculated in the process, or it can simply be used for soil amendment applications, right? And aqueous phase, right, it does contain some organics and ions, so it can be electrochemically treated to produce chemicals, or it can be kind of reformed to produce hydrogen gas, or the water can itself be used as a nutrient-rich water, okay, based on specific quality. Biocrude can be upgraded to biofuels, renewable fuels, and fine chemicals. Again, this would depend on the type of feedstock we are using. And of course, the gas can basically be it can be simply sent through a scrubber to majority of the gas here is CO2 because of the decarboxylation process that is occurring. And of course, we can use a scrubber to separate the CO2, and rest of the gases can, of course, on a larger scale, it can be fed back to the process. So this I would like to present as a summary of the whole of the whole presentation, right? And finally, acknowledgements to my students who have been working on all different topics, and to my collaborator who is especially working along with me in hydrothermal liquefaction process, and funding by a large group of large variety of industries, not only on hydrothermal liquefaction, but also on pyrolysis related technologies. Our HTL works have been funded mostly by Engineers India Limited and C6 Energy, who have been supporting us with, on the macroalgae hydrothermal liquefaction process. So with this, I would like to close and thank the organizers for the opportunity. And if there are any questions, I can discuss.
Any queries from the participants? Okay. Thank you, sir, for taking.
Am I audible, ma'am?
Yes. Thank you, sir, for taking your valuable time to share your knowledge with us. We now understood how a lot of energy is being wasted, as there is not proper utilization of agro waste, municipal waste, and how proper disposal and usage of these waste can be helpful in generating energy. We also understood what is hydrothermal liquefaction and its importance, and the advantage of hydrothermal liquefaction by crude. Thank you, sir. Thank you very much.
Thank you. Thank you.
Thank you, sir.
Ma'am, am I audible?
Yes, sir. May I now request Dr. M. Tukaram Bai to introduce. Thank you, sir.
Yeah.
May I now request Dr. Tukaram Bai to introduce Dr. Tallada Bhaskar Garu.
Ma'am, am I audible?
Yes, yes. Yes, madam. Yes, madam.
A very good afternoon to all. It's my great privilege to introduce Professor Tallada Bhaskar Garu, Senior Principal Scientist. He is currently heading the Material Resource Efficiency Division and Professor in Academy of Scientific and Industrial Research at CSIR, Indian Institute of Petroleum, Dehradun, India. He handles thermocatalytic and biochemical conversion of biomass along with sustainability impact assessment area. He has received PhD from CSIR, Indian Institute of Chemical Technology, Hyderabad. He carried out postdoctoral research at Okayama University, Japan, after which he worked there as assistant professor for 5 years. And he has 185 publications in SCI journals of international repute with the H index of 53 and around 8,670 citations. He also contributed 44 book chapters to renowned publishers like Elsewhere, John Wiley, Woodhead Publishing, CRC Press, Asia Tech, etc. and 14 patents to his credit in his field of expertise, in addition to 300 national and international symposia presentations. In addition, he is the project leader, coordinator for several projects for biomass and waste valorization. In view of his expertise, he is on the editorial board of international peer-reviewed journals and editor for 4 books. His areas of interest are thermocatalytic conversion of lignocellulosic biomass, lignin valorization, waste plastics including e-waste, novel catalytic materials, adsorbents carbons from renewable materials. Dr. Thallada Bhaskar Garu also received many prestigious awards. In 2008, he received the Japan and Most Progressive Researcher Award from FSRJ. In 2013, Distinguished Researcher Award from Association for Iron and Steel Technology. In 2016, he received Scientist of the Year Award from National Environmental Science Academy, NASA. Dr. Thallada Bhaskar Garu has received the CIS Presidential Award for the Foreign Fellows in 2016 and worked as a visiting professor. During 2009, he was also a visiting scientist to Tokyo Institute of Technology, Japan Society for the Promotion of Science. He is also the fellow member of many reputed associations like Fellow of Royal Society of Chemistry, Fellow of Biotech Research Society of India, Fellow of International Society of Environment, Fellow of Engineering and Sustainability, Fellow of International Bioprocessing Association, and also Fellow of Telangana Academy of Sciences. He received the Raman Research Fellowship for the year 2013-14 and was a visiting scientist at SIMTEF, Norway. In addition to all these, he has received several projects, grants from government, public sector and private organizations for carrying out research. As an organizing secretary, chairman, Dr. Thallada Bhaskar Garu has organized international events in India and also mini conferences in Pacicham in 2015 and during 2010 in Honolulu, Hawaii successfully. Dr. Bhaskar Garu is a subject expert in various committees under DST, TIFAC, NITI, IO, CII, etc. He is a member of the scientific and organizing committee of several national, international symposia in India and also in abroad and visited several countries to deliver invited plenary lectures and participate in technical deliberations. With this phenomenal biodata of Professor Thallada Bhaskar Garu, I hereby request Professor Sridevi Madam to welcome him. Thank you for giving me this opportunity. Thank you one and all.
Thank you, madam. Now I request Dr. Thallada Bhaskar Garu, IIB Dehradun, to deliver his lecture on strategic design of processes for effective utilization of waste biomass.
Is it visible, madam?
Yes, yes, sir. Yes, sir, it is visible.
Yeah. Uh, for inviting me to share and giving me an opportunity to discuss, and especially after the three speakers from different organizations and eminent researchers working in this area. From the beginning, Professor from the USA, Professor Tata, and Professor Pila Nageshwara, and also Professor Venu. I think the my presentation will be easy for the audience as well as for me. In continuation of the the topic on the solid waste management, I would like to share some of our experiences and the thought process in this very important subject, not only for India, at a global level, the strategic design of process for effective utilization of the waste biomass. And I am from University of Petroleum and working at Material Resource Efficiency Division. Why all of a sudden we have been discussing about the solid waste? Because there are certain resources on the earth crust which are finite, which has to be recycled back and used. You cannot grow more. Like any metal resources like gold or any element in the periodic table, most of these transition metals which we normally use. The other resources, renewable resources, you can grow, but there are certain limitations which also impacts on the food and flora of the further required for the global population in billions. So with this concept, we are working how effectively we utilize the resources available in a circular way, in a sustainable way, and how one has to design the mantra to start with the solid waste management one has to adopt the sustainable development goals. Otherwise, the present use of fossil based resources have been using, and we can use it till another 30, 40, 50 years next. Again, we will have some issues may be there, or some alternatives may come. But the adversity and the impacts of the use of the fossil as well as non-scientific treatment of the renewable materials has made the global community to sit on and devise a strategic formulas or the goals which are sustainable development goals. And these goals, if you see, each goal has certain objective. However, it also linked to the remaining 17. So we cannot work or we cannot have any industry or a thought process that, okay, I wanted water, so I can pollute any kind of a resources or any kind of a available things. No, it will not work like that. How it is interrelated, and now the present issue is basically for India especially, it is a energy, because due to the population increase as well as the GDP increase, we need to work on it. If you see a single energy central to the development, that is, if you see the goal 7, you can see how it is relevant or connected to goal 2, goal 12, goal 3, goal 1, goal 4, goal 8, and goal 6. Now you can see the different bullet points. Energy efficiency, renewable energy, universal energy access is the most critical, but which impacts the all other essential parameters for the livelihood, not for the economics. The scientific and technological interventions has to be looked into how economic benefit has to be obtained with the intervention of the scientific and technological thought process to use these materials transformations. What actually the resource efficiency? See, resource efficiency we can decide or define in two ways. Use the less resources by producing the same given output, or use the same given resources, increase the more output. So either you reduce the resources or increase the output. That is what normally we say crop yield per drop. That means using the same drop of a water, we need to increase the efficiency of the food. Similarly, the resource efficiency has to be convinced or improved for the resource efficiency. But we should not be restricted here. It has a lot of deep thought process in it if you see the efficiency. How it has to be connected to the circular or linear economy. Now we have been living ever since the human existence in a linear economy way, only looking at the economic developments, but at the same time we spoil a lot of environmental issues. So environmental degradation is beyond our control. Now, what actually the circular economy? Circular economy teaches us to develop the economy, but without the environmental degradation. So now what we have to couple or decouple the both is the economic development from the environmental degradation. This mantra circular economy has to be looked into. I will go through some of these slides, what actually the case studies, how strategically it has been utilized for the linear and circular economy. Now the issue is we have 1.3 billion population and we have a lot of developmental needs, we always talk, but the most usage of the resources has serious consequences on the environment. So the negative impacts has to be addressed. So that is why the efficient use of resources is essential for India in order to achieve. But most of the audience are students. So it is my sincere request to think about the thoughts, the way we have to address the solid waste management or look the solid waste in a different way. Otherwise, again, we will end up in a big problem than the mistakes we did from the last 50 years, 60 years by utilizing the fossil-based resources without doing any end of life cycle assessments or the end of life treatments being utilized for the fossil-based. With this brief background agenda, when we look at the national priorities, the Government of India and INDC decided that the 300 million no access to electricity, that we should provide the 24/7 electricity sustainable energy to all, and committed to reduce the carbon intensity 33 to 35% by 2030, that is with respect to the 2005 values, fossil fuels reduction, renewable power increase. There are several thoughts or the commitments which all directly or indirectly linked to the energy and also the bio-based. So I don't want to explain because several people explained about the present usage and the numerical values of the energy for India. Now, India is on the path of the self-reliance. Now, what actually we are thinking of is a biomass is an important resource in the process, and it is the renewable material, and it is an organic carbon. It is not the inorganic, it is an organic carbon. Why it is organic carbon? When we see the energy or the hydrocarbons being utilized today, whether it is a chemical or a energy purpose, it is basically the organic carbon coming from the fossil-based resources. With this thought, with this thing, we need to look at the availability of the organic carbon resources. So the renewable carbon resources are aptly suits for this. The reason is, whatever we call today the fossil-based resources, they are also the formed by the renewable resources only. If you see the history of the crude oil, if you see the history of the fossil-based, they have been formed below the earth crust several years back due to the pressure and the temperatures exerted and the available there. So it formed in the form of gases and the liquids. So with these things, we have been producing The same way, we can also produce the biomaterials, biochemicals, biofuels in the form of energy or chemicals using the bio-based resources. So now what actually the decarbonization, and we are thinking of the net zero carbon dioxide by mid-century. That is what the Honorable Prime Minister has conveyed from the Red Fort on the August 15th also, that we need to understand, we decarbonize the technologies across all sectors. How this will happen and how our young students who are attending the event should think of in the down the line to see by 2050 from now onwards. That is to understand the decarbonization processes for the electricity, and you can use the biomass and also the carbon capture, and also finally the hydrogen is also one of the best solutions, provided if you use the end of the life end of the emissions that can be sequestered or used for the different applications. The most important is the energy efficiency. If we improve the energy efficiency by reducing the carbon emissions, we need not worry or we need not depend much on the renewable resources too. That the reduction of the demand, that carbon intensive products, basically the heavy industries, that is the cement, steel, plastics, and the heavy duty transport, that is the heavy highways, and also the shipping and the aviation sectors. These need to be utilized by the hydrocarbons. These are the major, but there are several minor industries which also still are depends even after 100 years also. Considering this one, the strategic design of use of these carbon materials is essential. When we talk like this, when we assume that the decarbonization by 2050, what is the basis genesis for this? If we see the genesis, now today, as professors mentioned that today the import of the crude oils now approximately 220 metric million tons, and the carbon present is 85. If you see the carbon content is 190 metric million tons, coal around 150, in similar way natural gas. So the total imports are approximately the 350. If we are able to find approximately the 350 metric million tons of carbon atoms, I am not talking about the hydrocarbons, because even the crude oil we process downstream. Being a scientist at Indian Institute of Petroleum, how many different downstream process will be there to make the fossil based crude oils into a transport or the liquid fuels? So that we need to think of. If we see the available carbon resources in the domestic or in India, it has more than 500 metric million tons of the waste carbons. Now you can see here the agricultural residue is a minimum level if we assume on 120 metric million tons, forest residues, biogas, municipal solid waste, used cooking oil, there are so many, and these values I have taken at minimum. If you can see these things, you will have more than 500. With this, we can meet the energy requirement and sustainability. As I mentioned that biomass and the efficiency improvement, manufacturing process need to be circular so that we can do. What are the available options, as Professor already mentioned, so I will not explain or take much time on this. There are several resources, first, second, third generation biofuels based on the feedstock, and being a 1.3 billion population, we cannot depend on the edible materials, so we should only look for the second generation, which are non-edible biomass. As a scientist, as a National Task Force Committee member working on the National Biomass Policy, and the National Biofuel Policy says clearly that the reduction in oil imports by substitution with renewable fuels, 20% blending of bioethanol and 5% biodiesel by 2025. You might have seen several news articles recently, the ethanol blending now all over India, it is already around 8% blending is possible and it is being practiced due to from the different resources, and achieve the 35% reduction in the energy emissions. To address this one, if you see that we have more than 260, 270 surplus biomass available metric million tons, 270. And now you can see that this is more than much available. This is a 2019 report, and now recently we have released another report in 2022. If we see this one, there are different varieties of biomass residues, basically the wheat straw, rice straw, cotton straw, and maize. some part the grain around gram, that is also around 6%. When we say biomass or the non-edible biomass, it is not like a other. It is similar to other fractions or other resources also. When we say crude oil, all crude oils are not same. The Australian crudes, Vietnam crudes, and the Gulf crudes are completely different. We need to do some pre-treatment process in order to make suitable for the downstream process. So similarly, there are differences in it that we will discuss in the coming slides. So the total annual crop residues around 700 metric million ton surplus, as I mentioned, around 200. We need to convert this one into different products required. So that means locally available resources for the local applications and the local demand. As I mentioned that the demand and supply both matches, or the supply is more than the demand, then what is the problem? Now you see that the different climatic zones available in India, the biomasses available and the type of biomass available are not same. Now you can see the typical biomasses available, as I mentioned here. These are typical 10-11 biomass reports we have taken. Practically, we have analyzed these biomasses, worked for different conversion process. Now you can see here the available data. If you see the lignocellulosic biomass, which is basically the composed of the three main polymers, that is cellulose, hemicellulose, lignin, the same type of the biomass like cellulose, hemicellulose, lignin, much variation. Now you can see that the New Delhi biomass is 5.54 and the Palakkad biomass has 30% lignin. Now you can understand, we cannot take the lignocellulosic biomass. Lignocellulosic biomass is uniform. No. Now you can see 30% lignin and 5% lignin. These two biomasses you cannot process by adopting a same technology. This is a small indication I am telling. Now you can see the cellulose, which is basically the primary constituent for the ethanol production. The difference in 33 to the 41, it is around 10%, 8% change. When you see the downstream process of the 100 KT ethanol production plant design, it is tough. You cannot design a unit for so much variation of the cellulose, because the downstream process will have lot of variations. So the strategically map the availability biomass to the optimal process to desired product. Now, if we understand down the different biomasses, now you can see there are grass, softwood, hardwood. Now you can see that synapyl alcohols, which are primarily the available in the plants, grass 25 to 50%, softwood is only 0 to 1%. Here it is 50 to 70%. The typical examples now you can see here. That means the grasses, softwood, hardwood, all are biomass, but the composition of the monolignals present here, SGH units, are completely different. This is another typical, the most important process you have to understand, or the composition that is much different. As a chemist, applied chemist, now I can explain more that the softwood, hardwood, if you see the bondings, is a much difference in the composition of the different biomasses. That means if you see these different variations, the chemical structure of the phenol remains same, but the bonds present here are completely different. With these deviations, now you can see the OH phenolics 20 to 28 in softwood, 9 to 20 is the hardwood. This much variation, you cannot design a single process to make it a same yields to design, or the benchmark, or the viability of the process, or the commercialization process. Now you can see the kind of the bonds present in the different biomasses. So with this concept, with these complexities of the biomasses, the title of my presentation defined as the strategic design of the biomass for the production of the chemicals or the fuels, or the national domestic requirement purpose. So with this, we are making a information biomass availability to see on the different states, and this is a report available with the TIFAC, and this report recently we have published, and with the collaboration of the space satellite data with the Jai Urja, it is from the NRSC government of India, so that this dynamic data is available, so that the design of the processes across India, approximately 623 districts, we have been matching. Now, what is possible with the complexities available here? Technically, chemically, you can produce all the process products here, but the basic platforms for both the biomass conversion, all this is biotechnological, thermochemical process or thermocatalytic process. We like to explain the unestablished or the developing process much compared to the ethanol, which is at the demonstration scale of the large scale processes here. I will take you some of the studies, which the experiments are the studies done at our laboratory at IIP. We have been working on the carbonization, biomass to chemicals, different pyrolytic processes based on the feedstock, slow and fast, hydropyrolysis, liquefaction, that is hydrothermal liquefaction, and also finally, wherever it is possible, try to upgrade to the bio oil, to the fuels and chemicals. And last but not least, the kinetics and thermodynamics, because after the laboratory scale study of the 1 kilo reactor or the milligram level or the gram level studies, we need to do the ton scale, at least ton scale, because of the decentralized, having the advantages in the decentralized processes. We develop these different models. This is the typical flow chart. Once we have the biomass in the laboratory, we do the kinetic parameter estimations using the pyrolysis methods, and also they understand the PyGC mass and the lab scale process of the pyrolysis, whether it is a slow, fast, hydro and hydrothermal, then product analysis, then understand what product possibilities to utilize these products, what is the opportunities for the upgradation. Then we understand the characterization, different sophisticated methods for the feed as well as the products. Then we design the strategy. This is a typical role of thermogravimetric analysis. As a student's chemical engineering, this is a much important to understand the data using the artificial intelligence or the Python programs or the different data sets to make use, understand the mechanisms, kinetic triplets, which is required for the process scale up. We do this kind of the mathematical treatment of the kinetic analysis by estimating the 3 different triplets and also design the different models. Otherwise, if we don't have a models, all biomasses cannot be operated with the same reaction parameters to obtain a suitable product. Now you can see that with the change of the conversion, how the product portfolio, product profiles will change, how the kinetic triplets will change with the conversion. It is not like a conversion of the simple compound like benzene to the phenol or the ethane to the ethylene, that throughout the reaction always the endothermicity or the thermodynamics remain same, so that you can control the reactor. But that will not take place in a conventional or the thermocatalytic processes. Not only this, in other process also with the biochemical process, you need to design or pre-treat the materials so that you can control the energy, heat and thermodynamic balance. So we do the different master plots using the several mathematical treatment. Then we have published several data and designing our own models to see that it fits to the more than 99. Now, with this background, analytical background, we are trying to use the available biomasses at different places at the fields. This is the Punjab, where I'm standing in front of the huge quantity, where you can see that the several newses during the winter, the burning, stubble burning in northern India, Punjab and Haryana. We are trying to use these kind of the biomasses to make the pellets. Every material cannot be made pellets so easily, like our vermicelli. Every rice straw, rice flour or the other flours cannot be made. Similarly, the required strength, required properties, required things cannot be utilized. So the design of the burners, design of the pelletizers has been done for the different applications used in the fields, and we are supplying this torrefied or the pyrolytic materials or the biochar for the applications in different places. Similarly, as Professor already explained about the hydrothermal conversion process, I will not discuss much, because I will explain you the case studies which we have done. It has a lot of advantages, as Professor explained. Our studies are the field studies to apply this one is the invasive aquatic species valorization, that is from the Imphal, that is in the Loktak Lake. It is only the lake which is in the world floating lake. These floating lake, because of these species, it creates a problem due to the paragrass, fumdi, and the water hyacinth. We are trying to take out this one. We have did work and we have published articles and the patents and they generated the knowledge base for the conversion of these materials to produce the value addition compounds, functional chemicals using this. Now, the next feedstock, which normally is the most important with the 2G ethanol, is coming into the picture. In the ethanol industry, only the cellulose is being utilized for the production of the ethanol, but the remaining lignin, which is unutilized presently, it is burned for the energy applications within the refinery, within the biorefinery. But this is the most important carbon material. Burning of this material need to be stopped to use by using the other materials. So the process for the lignin valorization. See, the treatment, there are several processes, but the lignin which is being produced by the different process will have the different functionality. They are called different lignins. They are not, all lignins are not same. So we are trying to utilize using the different approaches. If the biomass treatment is 10 varieties, then the lignins also 10 varieties. So we need to utilize the different methods to convert these materials. I will tell you the simple case study and example how is two different lignins like prot and the alkali lignins. These two are the industrially available lignins. To convert the hydrothermal during the catalytic processes, you have the vanillin and also the acetoserangone for the prot lignin. But when you design a process, alkali lignin, you have only vanillin, you don't have the acetoserangone, and the quantity of the vanillin is very high. Vanillin is too expensive, and the natural vanillin is much in demand. This is coming from the waste lignin from the industry. Like this, we need to strategically design what process, what catalyst, what condition, what is the downstream process that need to be adapted to produce the vanillin or the acetoserangone, such a valuable chemical from the waste resources. These studies indicates that the design is very important, what kind of feedstocks. But we cannot generally say that this feedstock is suitable for the HTL or this feedstock for the pyrolysis process. So we are trying to utilize these. Now you can see the HTL basically applied to the micro and macroalgae, de-oiled cakes, invasive water species, as well as the lignin, as I mentioned now. But the problem is, when we wanted to use these kind of stubble burning at the fields where the feedstock is available, sparsely small quantities with a large distances, how to collect, how to treat? That is what the problem is. Supply chain management, logistics. If the energy consumed is much than the energy produced in the process, then the conventional process will not work. So the idea is the mobile units, mobile conversion units, so that this mobile unit will go to the field where the biomass will be converted and given the char as well as the energy products there in the field. That will be applicable, that will be used for the enhancement of the organic carbon in the soil, so that the product will be more and we can convert into the fertilizer based food to the organic farming by using these carbons, because the amount of the environmental issues as well as the economics required for the scale is not met today. That is why we are trying to use these applications using these decentralized approaches, because these applications are much valuable of the different oils. We are working with the industries. Now you can see that these pyrolytic oils are used for the herbal animal healthcare products, and this industry has around 35 countries present producing and using these pyrolytic oils. But this pyrolytic oil process is different from the conventional feedstocks, also different, where the Patal Ganga, Patal Tantra, Patala Yantra process, as well as our typical Ayurveda is based on the plant-based materials. We are working with this to produce these different biomass resources, and these activities are very good. Not only that, as I mentioned, that 1.3 billion population, we need food, organic food, and several governments has issues because of the onion prices. We are trying to increase this pH free biochar to increase the yield of the onions, as well as increase the applications of these for the snake repellents, termites, fungal residue, larvicidal, other pest repellents using these bio-based components, because the present today use of these fossil based chemicals has the serious effects, and the market for those things is also difficult. Now we need to domestically available resources find the applications for the domestic demand, so that we need not import any outside products and use the renewable materials. Not only that, we are also trying to use the other things by using the different process. In addition to the case studies, we are trying to do a different fundamental studies with the help of the 30 odd students in the laboratory to understand the diverse feedstocks using the different hyphenated techniques. Now you can see that this GCMAS, the pyrolytic GCMAS method, to understand the different lignins, heterocycles, aliphatic carbons, and the phenolics from the different catalytic methods which I have explained. Now, not only the typical one compound, we are also trying to see the increase in the concentration of the Goa cells as well as the other components with the different lignins. Not just the hydrothermal, we are also trying to see with the pyrolysis also, so that the value addition is possible in different alternatives, not by one method. Because if you produce a one chemical a large quantity, there will not be any market, then we will have a problem. So we need to see the supply demand as well as the resources availability and efficient conversion. In a similar way, we have also adopted the process for the oxidative process, because the demand for the simple acetic acid, vinegars, formic acid, and several other oxidation products are much in demand if you see the government of India's data. So we are trying to convert that, and we generated the data and also the catalyst prepared to convert the oxidation products. In any of these dry and the wet process, we definitely get the biochar. But the pyrolytic biochar, which is a simple biochar, the hydrochar, which is produced by using the hydrothermal process, is different. Because the much of the carbon percentage is not converted, if in the processes you will end up a product that need to be utilized. Today, the demand for the purified carbon or the carbons for the diverse application is much high. Morning professor mentioned about the drinking water issue. Today, all of us use the carbons for the water treatment. That carbons we need not import, that need not be fossil based, that can be produced using the waste feedstocks available across. But the parameters, forest structure has to be generated in an optimized process for the commercial feasibility. With this, we wanted to have a model, decentralized small scale units to process the liquids. Then once we have the decentralized units convert in a centralized process, then the decentralized approach, then we need not transport the small density of the low dense materials like biomass for the large distances. Once you convert into the oil and char, the heavy dense materials similar to the crude oils can be transported to use the existing refinery infrastructure, then produce the different process. In a cyclic circular manner, you use the agricultural waste, harvest, then use the thermochemical process, use the energy, and also enhance the carbon in the soil, produce the more food. So that in a circular way, we can increase the economy of the farmers as well as use the resources, avoid the import of the fertilizers. We need to study different case studies. The different soils have the different environments effects, as well as the different biomass available. I am working in several districts in different states in India to apply up the different models. This is a typical case study with the funding of the Global Challengers Research Fund with the different NGOs. It is called the GCRF fund. In a disadvantaged rural areas of the Odisha, we are trying to generate this for the biotrig model, so that we produce all kinds of the products which is required in the districts. This study we wanted to do enhance much on the biochar for the soil amendment with the help of the ICR people and the agricultural people, so that this can be done. Without the proper understanding of the biochar, every black material is not biochar. If it has the lot of pH, it will kill, it will spoil the entire soil. It will become a more useless than the existing. So one has to be careful how carefully one has to be convert these kind of the materials to use as a biochar for the soil. Not only that one, you can use the different applications of this biochar. I will tell you some of the case studies. As Professor mentioned about the biochar for the energy, we use this biochar for the different catalytic applications. Catalysis is a different phenomena. It has lot of porous structure. You have the active components, active metals impregnated on the materials. We used this kind of the pine needle. I am in Uttarakhand. It has lot of pine needles. It has a forest burns. Then forest fires can be avoided by use of this one to make the convert the pine char. It has very special, and using this special biomass decorate with the ruthenium nanoparticles, convert this into a catalytic material. This is highly demand product today, and this is not imported catalyst. Today we are importing the huge quantity of the catalyst from abroad. So using this typical available resources, using the basic fundamental scientific principles, you can generate and you can produce the data that recently we have generated, published a big article on this, how we can translate that. Similarly, a cellulose can be converted into the methyl alpha and methyl beta glucopyranidazide using the carbon-based catalyst. That is a product which is obtained in the form of a biochar. This is very expensive material. This is small quantity required, but the catalyst being presently used is the imported material that we can avoid by using this biochar. Not only that, once you purify and identify certain feedstocks, this functional biochar can be used in the electrochemical applications, and it's a lot of potential. But the functionalization, using this for the, whether it is a hydrogen generation or for the electricity generation, using the small scale process, because the demand for such kind of materials is also very small. Every biomass is need not be produced this kind of a material. Using this, we are producing the specialty carbons for as a supercapacitor applications for the electrode. Now you can see that a typical biomass found in the India has very high specific capacitance, which is not comparable to the even other materials. This is a waste material. Optimized this to use as a capacitor applications. Similarly, the lignin, as I mentioned, the much more component and the 25 to 30% of the lignin in the lignocellulosic biomass, which is not used, as I mentioned earlier. There are several applications of this. We are trying to do that by understanding, optimizing this one, but there are several challenges in terms of the feedstocks. There are availability and the kind of the biomass and the sustainability design and renewability. If this is not there, it will become a challenging. We need to understand the basics of the thermodynamics, basics of the photosynthesis process, the amount of the biomass burnt or the converted, the photosynthetic efficiency to produce the biomass should be same. Otherwise, we will have more serious consequences than the climate change happening due to the use of the fossil-based resources. So that we need to understand the issues also. But what is next? There are several strategic choices to be made for the biomass utility. There are environmental issues, social issues, economic issues. Otherwise, we will not address the sustainable development goals. You need to understand. So the competition between the different biomasses that might need to lead incoherent policies and the serious implementation issues. Otherwise, we will end up in other issues. The strategic design, strategic application is essential. Otherwise, every waste material cannot be produced using the pyrolysis or the slow pyrolysis or the hydrothermal. Otherwise, the economics and the end use of the products and the downstream separation process is most essential. So the energy is the most maximum required commodity, but the low value. But the biomaterials without much decomposition can be produced to have these carbons like that with high specialty carbons. Biochemicals, which are also much in demand, but compared to the energy products, the biochemicals, only the 4 to 6% of the fossil-based crudes are converted into the chemicals. So the demand is less. Biofuels very high, bioenergy is very high. So the renewability, sustainability, circularity need to be looked into. I will not take much time. We'll take a few minutes to complete the plastics issue, because when we talk of the biomass or the bio-based materials, plastics is also part of our everyday life. Now, not only the simple recycling, we can do this upcycling as well as recycling and downcycling. What actually the recycling is, you are closing the loop. Upcycling means not immediately the closing the loop, but you are increasing the value. Downcycling means the value of the produced product is much lower compared to the original material. But environmental factor, environmental issues need to be considered in all these cases. I will take you one simple case study. Now you can see this upcycling. If you have a simple PET water bottle, you make two pieces, use this for the water purpose and this for the lighting or some example. Now the value of this is increased much. The applications are more different. So the value is more here. Recycling means you are trying to make the PET bottle to the another PET containers of the bottles. This is you are trying to do the recycling with a similar value. So you can see the another example, this recycle and upcycle. Now you are making this old discarded cloth materials into the bags, not without much destruction or the tertiary recycling, you are making the value. That is why we can see that there are several materials in the showrooms that the recycled products which looks very nice. By using the design artifacts or the skill set, you can make the more value using these materials, because the polyethylene terephthalate is material without much additives, no impurities. It is a pure materials. So that is why plastics should not be looked in a different aspect. They are best materials, but the end of the life treatment is very much essential. That is why I call it as a plastics as a gold materials, provided if you properly use at the end of the life. So the upcycling and the circular economy is a different. So you need to do in a upcycling way, close the loop, but with the value addition. That is addressing the 12 sustainable development goals. This increases the waste to the landfill is reduced. Otherwise, what happens in any circular process, even a certain quantity of the unused in the process will go in the landfill. That creates also problem. That's what I have been telling, that the resource efficiency is a key material. Environmental cost has to be added. If we don't add the environmental cost, then it is difficult. So the developed nations they are paying the tax for the environmental issues, but we are not paying. The taxpayer base is also very less. Otherwise, we cannot address, we cannot compare. Our situation is different. The country's demography is different. That we need to understand, find the better applications using the scientific technological base. So the upcycling options based on the catalytic transformations also, that eventually the have the best opportunities. There are several case studies. The last I'm talking about the electronic waste, because I am working in this area also, the plastics and the electronic waste. Now you can see this, as I mentioned in my initial address, that there are materials cannot be renewable. Now you see a typical telephone, mobile phone, around 50 elements there in our periodic table. We cannot grow these materials. And once we discard this without any scientific method, we will have a serious issues. That is why in the introductory, professor mentioned that the Japan has developed the processes, some processes to treat for the production of the Olympic gold medals and the silver medals and the bronze medals. We need to adapt, we need to improve the processes for the available waste materials in India. And the reasons why we cannot directly take some of the process are the kind of the resources, kind of the concentration of the metals available is different, and the processes, you cannot take the process one available to the different concentrations of the metals. So strategically that need to be obtained. And as a students, you can realize it is a 2002 and 2003 data of the 315 million computers that may become obsolete. Now you can see the kind of waste might have generated, that is 550 10 to the power of 6 lead, this much cadmium, silver, mercury, chromium, and plastics. Now you can see, and brominated flame retardants. All our electronic components, including the mobile phones, refrigerator, washing machines, have the plastics with flame retardants. It has the bromine, it has inorganic content. it will create a more problematic things than the climate change. Immediately this will affect to the flora and fauna, even our systems. There are already several places which has a lot of impacts. That is why the sustainable and the strategic design of the treatment is essential. I have been working from the last 20 years in this, even just in the plastics and e-waste, 36 journal publications and patent on the plastic valorization, several book chapters on the e-waste and the PVC mixed plastics, and also working as a nodal officer for the projects, mega projects on the plastics and other waste materials. But finally, the future of the biomass in the decarbonization and the strategic design statements are renewable energy for the electrification, for the solid bioenergy, that is 60% that is going to be, and the preference where direct electrification is difficult, like cement industry, 30% of the liquid fuels for production of the biomass to help sectors like aviation fuel and marine, or use the CCUS or BCCS, that is the carbon capture, utilization and the sequestration, or the bio-based. There are several these three pillars that need to be adopted among the global, and India, we need to adopt some of the things as per our availability of the resources and the combination of these. But for that, we have a challenges. The quantitative, qualitative data on the availability and particular location is being need to be generated and made it available. Work is in progress. Different barriers during the conversion, that is effective, efficient reactor design, stable catalytic materials for the conversion as well as the process, complete understanding of the decomposition mechanism and the market demand. We have done a lot of studies for the different companies across the globe and different US agencies, and also life cycle assessment. Otherwise, what happens at the end of the life, this will have more environmental issues or the resource efficiency issues compared to the present problems that need to be adopted. So we have several publications to treat the PVC mixed plastics and the several publications on the biomass for the different applications, hydrogen purpose, gasification, catalytic materials, algal-based biofuels, and the different approaches also. But when you see in the market or when you see in your lifestyle, you can see the complex materials at one place. That is why we call it as a waste biorefinery. Now, 4 books in this series has been established. We are working with our experimental data, trying to understand what are the best strategies. And the next book will be in the month of December or January, to make sure that some of the processes can be adopted in the several places in India. We are working with the different industries to contribute the knowledge base to treat these materials in the different. But without the sophisticated hyphenated equipments, you cannot generate the reliable data for the conversion of any of these complex waste materials. It is not like a rice mill. You have only rice, then you process, you produce this one, rice and the husk. But the complex material to treat in a chemical industry, you cannot. That is why we have issues with the economics. We have a end of the life materials. We have the landfilling issues. Segregation at stage is very essential. Without that, we cannot succeed. Otherwise, everything will go to the energy. Value addition is not possible. Why the so many plants are not working, even though we have established around 11, professor mentioned about the 6, because the non-scientific approach, non-scientific way of thought process to just make the money without understanding the complexities or the science behind it, we cannot work. So these analytical tools will help you to design the process, strategic understanding for the different products obtained, whether it is organic, like waste base, or the solid biomass, or the compositional purposes. We use these kind of things to address the strategic design of the different materials. Whatever it is possible to explain in a time limit, I have explained. But finally, the statement that if we don't do our scientific work, someone else would do. But if we neglect our social responsibilities as a scientist or the teachers, there would be no science. So particularly in the era of the 21st century, of the energy problems or the climate change problems, so the solid waste is intrinsic part of this. If we don't understand the realities or the intrinsic issues, then we will be failed at the large scale issues. With this, I thank once again all my lab members, funding agencies, people who made all the contributions to work it, and also the organizers and the patient hearing of all the audiences. because it is already last presentation of the event. And with this, I would like to stop, and I would be happy to answer and try to answer and maybe think over and again come back with my answers to all the questions. Thank you very much once again.
Thank you, sir. Any queries from the participants? Thank you, sir. From your valuable lecture, we have gained knowledge on what is sustainable development and how biomass production and self-reliance are interlinked. There are different energy technologies which should be put into practice to produce biomass